The title of my presentation is KUKA Sunrise Toolbox, Interfacing Collaborative Robots with MATLAB. So the KUKA Sunrise Toolbox is a library that allows controlling KUKA collaborative robots from an external computer using MATLAB. If you ever used MATLAB, you know that it is extendable with external libraries called toolboxes. Using our toolbox, you extend MATLAB to control KUKA collaborative robots. So the toolbox is made available online, free for use, under MIT license. So feel free to download the code, to use it, or to modify it. The idea is to achieve the highest scientific impact. The toolbox contains source code, documentation, and links to video tutorials. So anybody with basic knowledge on MATLAB can start using KUKA collaborative robots in a minimal amount of time without requiring advanced knowledge on how to control industrial manipulators. Our toolbox contains more than 100 different functions divided into 6 main categories, including networking functions used to administer the network between the robot and the external computer. There are also real-time control functions and point-to-point motion control functions, which are used to control the motion of the robot. There are setters and getters functions that are used to read and write the different parameters inside the robot controller. There are general purpose functions that are used to calculate forward kinematics, inverse kinematics, the dynamics of the robot, and the various matrices of the manipulator, including mass matrix, the Jacobian, Coriolis matrix, centrifugal matrix, null space projection matrix, and other quantities. The toolbox also contains physical interaction functions, which include 2 different hand guiding modes in addition to touch detection. In the real-time motion control, the user is able to control the velocity and the direction of the motion in each instant. This is important when the trajectory of the motion is dynamic and changing. For example, in the collision avoidance system, where the trajectory is changing according to the minimum distance between the human and the robot. In the point-to-point motion functions, the user is able to move the robot on a line, on a circle, or on an ellipse. In such a case, the user defines the destination point and the motion parameters, and the robot is gonna move. The toolbox also contains physical interaction functions, which include 2 different hand guiding modes: the hand guiding in the joint space and the precision hand guiding at the Cartesian space, as you can see in the video in here, where the user is able to move the robot along the X and the Y and the Z axes while keeping the orientation of the end effector fixed. Also, the user is able to change the orientation of the end effector while keeping its position fixed. This is very important in precise assembly operations. By attaching a force torque sensor at the end effector, the user is able to hand guide the robot in equilateral environments. In such a case, during a contact between the robot and surrounding obstacles, the robot is able to slide with its body on the structure of the obstacle while keep moving according to the hand guiding command. The physical interaction functions also support the touch detection mode. In this example, the robot is performing a pick-and-place operation. When a collision is detected between the robot and the surrounding environment, the robot stops and waits. When a double touch is detected in the last link of the robot returns back to performing the operation. The toolbox also contains example code on how to integrate simulations for controlling robots. The real robot is performing the motion in synchronous with the simulation robot. Nowadays, I am using the toolbox in order to experiment with 3D printing using cookie collaborative robots. In this video, you can see that the robot is performing 3D printing of a miniature of the first stage of the Saturn V rocket. This was as a commemoration of the 50th anniversary of having a man land on the moon.